Welcome to your next lesson, which is linear versus nonlinear. Okay, so the first little piece of notes that I want you to write in, and it'll make more sense as we go, I pinky swear, is let's just first talk about what linear means. In order for something to be linear, it has to have a constant rate of change. Constant rate of change. Okay, and we're going to be exploring this phrase a lot today, rate of change. Rate is a comparison of two things, and in this case, it's going to be X and Y. Okay, so how X and Y change in comparison to each other. But this is the mathy definition, constant rate of change. It is very important, so like maybe bubble this, highlight this, whatever you want to do to make it stand out. But for something to be linear, it has to have a constant rate of change, okay? It'll make more sense as we go. Pinky swear. So I keep saying in order for something to be linear. What do I mean by something? Well, there's three relations that we're going to look at today. We're going to look at graphs. We're going to see if graphs are linear or nonlinear. We're going to see if equations are linear or nonlinear. And then we're going to look at tables, so XY tables, and decide if they're linear or nonlinear. Okay, so we're going to start off with the easiest one, which is graphs. Okay, it's very easy to tell if a graph is linear. So let's start with graphs. Okay. Now, linear literally has the word line in it. This is why kids pick it up so quick. In order for a graph to be linear, it's got to be a straight line. So what that means is if there's any sort of curve to it, it's not linear. It's nonlinear, okay? So the note that you need to have to yourself is must be a straight line. Okay, it's just got to be a straight line. If it's a straight line, we can call it linear. If there's any sort of curve to it, it would be nonlinear. The reason why a curve would make it nonlinear is because the rate that it changes. So it would not have a constant rate of change if there's a curve to it. So let me show you some examples. You're not going to draw these in. We will draw some examples in. But I just want you to kind of view different sorts of equations, okay? These are all algebraic functions, and a function is just a relationship between X and Y. And you'll notice that each one of these has an X and a Y in it somewhere, okay? Now, some of these might look a little scary, like sine, cosine, tangent. We're not getting into that. We're not doing any logs in my class. The only types of functions you'll probably see in my class are these two, okay? Now, right here, it says y equals x. That's just it's called the parent function, the basic function. It's not vocabulary you need to know, but right here, you can see that in this equation, when you put it on a graph, it ends up as a straight line. And that's because x and y are having a rate of change that's constant. Nothing is changing about it. Right here, like if you remember what slope is from 8th grade, the slope is not constant, it changes. So as soon as there's a curve, any sort of curve means your rate of change changes, okay? The rate of change is not constant here because it changes direction again. This one does a lot of loop-de-loops. It's definitely not constant. So constant means straight, okay? If it's a straight line, we can call it linear. This one has a little bit of curve to it, therefore it's non-linear, all right? The other type of function that kind of gets kids is, this is an absolute value function. This is just another example of how many different types of functions there are in algebra. but we're mainly looking at linear functions in my class this year. But this one, it's an absolute value function. If you remember, absolute value are those bars. When you graph an absolute value function, it looks like a V. It is made up of two straight lines, but in order for a graph to be linear, it's got to be one continuous straight line. It can be negative, it can be positive, but it's got to be straight. So another example of linear that's not on here would to be if it was like this, okay? It can be going down. As long as it's a straight line, it's linear. It's good to go, okay? Another example of a straight line that's not on here would be if it's literally flat. If the line is flat like this, that's still linear because it's a straight line, okay? So graphs, pretty easy to tell if a graph is linear. It's just gotta be a straight line. So we're gonna do 3 quick examples so that your notes have it. So once you set up little, these are gonna be teeny tiny X, Y coordinate grids. We'll do 3. X, Y, X, Y, X, Y. Pause the video if you need to, if I'm going too fast, okay? So once you have your 3 grids there, we're just gonna do 3 quick examples of what linear might mean. So on this graph, just go ahead and just draw a continually straight line. Arrows at the ends. Since that is a straight line, what that means is the rate of change throughout this entire graph is constant. X and Y are changing at the same ratio or the same rate throughout the whole equation. Since it has a constant rate of change, we can say that it is linear. Okay. Another graph you'll be seeing probably trimester 3 in my class. It's called a quadratic function, and it ends up looking like a U shape or a parabola. So like this. Okay. That is a very common equation, quadratic equation, but does it have a constant rate of change? Is it a straight line? No, there's a curve to it. So this is non-linear. Okay. And then I'm going to challenge you a bit. I want you to see if you can figure out if this is linear or non-linear. Here's your graph. What do you think? Is that linear or non-linear? I do see 2 chunks of straight lines, right? Like from here to here, that has a constant rate of change. From here to here, that has a constant rate of change. But the whole thing together, is the whole thing together one big straight line? No. So this is non-linear. All right. So it's pretty easy to tell if a graph is linear or not. You just have to think about, oh, linear means straight line. Okay, it's got to be one big straight line. It can go down, it can go up, it can go straight across, but as long as it's one big straight line, that's linear. Okay, and that's what we're dealing with trimester 2 is linear equations. Speaking of equations, that's our next little thing we have to look at. So we know about graphs, let's think about equations. Okay, so how do we know if an equation is linear or not? Now, the equations we're going to be looking at, here's some examples, are always going to have X and Y in them. Okay, and notice that Y is always on the left-hand side. That's very, very common in mathematics. Okay, but out of all of these that were printed, ignore my 2 that I drew up there, the only one that's linear is which one? The rest of these all have curves to it. It's not one single straight line. So something to notice is right here, when X was squared, when Y was cubed, that caused curves to happen, okay? When x was to an exponent of -1, that still caused some curves to happen. When x was raised to a fraction, that still caused some curves. So basically the only time when x, or when the equation was straight on the graph, is when x was raised to a power of what? What is the exponent on x? Don't say 0. Technically, if nothing's there, it's raised to a power of 1, okay? So that's going to be basically what we go with. Now, there are some exceptions to that, but we're going to go with that. X is raised to a power. If you don't like the word power, maybe write exponent of 1, okay? So if it's raised to the power of 2, nonlinear. If it's raised to the power of 10, nonlinear. If it's raised to the negative first power, it's nonlinear, okay? So raised to a power of 1 is kind of what we're looking at. So let's see if you can try this out. We're going to write stuff in our notes, but before we write it in our notes, I want you to kind of practice. I have some equations here, and I just want you to kind of go through the list and see which ones you think are linear. Here's what you're looking for. You're looking to see which ones have x raised to the power of 1. Now, reminder, if it doesn't have an exponent, it has a secret exponent, which is a secret exponent of 1. So in this case, this first one's linear. It doesn't really matter what else is attached to it. I'm really just focused on the x, and I'm looking up the exponent on the x. Since there was no exponent, there was a secret power of 1. Therefore, it's linear, okay? So I want you to go to this, and in your head, tell yourself, linear or nonlinear? X is raised to the third power. Has to be raised to the power of 1 for it to be linear. This one, y equals 5x. So you look at the x, what is it raised to? What's the power on it? What's the exponent on it? There's nothing there, so there's a secret 1. So that's good. That's going to be linear. If you were to graph that equation, it would be a straight line. Okay? Think about this one. Linear or nonlinear? Is x raised to the first power? Nonlinear. This one. I don't even see x. I don't even see x. Let's skip it. We'll come back to that. This one. Look at your x. Doesn't matter if it has a negative in front. We care about the exponent. What's the exponent there? There is nothing, but there's a secret 1. That would be linear. That'd be a straight line if you were to graph it. Okay, look at this dude. X is raised to the negative first power. Is that going to be linear or nonlinear? Nonlinear. And then, y equals -2. There's no x. So we need to figure out what happens if there's no x involved. So I'm going to show you on a graphing calculator. If I were to type in, and it's already got my y there, y equals 8. I'm going to graph that for you. Oh my gosh, it's horizontal, it's straight across. But is it a straight line? Yes. Okay, I'm going to go back, and now I'm going to delete that, and I'm going to graph y equals -2. Graph. There it is, straight line across. It is linear, okay? So when there is no x there, and it's just a constant, remember we've heard that number before, if y is equal to a constant, that's going to be a straight line. It's going to be a horizontal line, okay? Okay, so let's make a little table here of, let's say linear, nonlinear. We'll make a little chart. Okay, just so you can see some examples. So x raised to the power of 1. An example of that would be like y equals 2x plus 5. That's a very common equation you're going to see, okay? That's called slope-intercept form right there. X, if you just look at x, it looks like there's no exponent on it, but there's a secret power of 1. So that would be linear. It'd be a straight line if you were to graph it. Okay. We also learned that there can be a negative in front of x. That's totally fine. Okay. And you don't even have to have a +5 or a -5 or anything after that. You could walk away right now and that would still be a straight line. I'll prove it to you. I'll put it in my little graph here. Y equals negative, where's my x? Where is my x? There. Y equals -x. Straight line. Okay. And then we also learned that y can just be equal to some constant number. There's no x involved. So if we had like y equals 3, that'd be a horizontal line going across. Okay. Now, nonlinear would be like if it was y equals 2x to the third power minus 10. You can even put that on there. Point is, your x is raised to some power that's not 1. Therefore, it makes it nonlinear. If you had y equals x squared, that would be nonlinear. It would be curved. If you had y equals 5x to the negative first power, that would be nonlinear because it's raised to a power that's not 1. Okay, so equations, pretty easy to see if it's linear or not just by looking at the value of x. If x is raised to the power of 1, yeah, it's linear. Okay, so linear, straight line on a graph. For equations, in order for it to be a straight line on the graph, x would have to be raised to the first power. Okay, so if x is raised to the first power, it ends up as a straight line on the graph. Okay, now we get into tables. Tables. This is where it takes a little bit of time. Okay, so graphs is by far the easiest. You look at it. If it's a straight line, it's linear, right? So if I have an XY table, so let's set up an XY table. An XY table is just a bunch of ordered pairs, right? So something I could do is take those ordered pairs and plot it on a graph. And if the graph is in a straight line, then it's linear, right? So that's what I'm going to tell myself here. Graph x comma y values. Okay, you can write ordered pairs if you want to, but I'm just going to write that. Graph x, y points and see if the graph is a straight line. Okay. Ooh, there is some lag. Sorry about that. Graph x, y points and see if the graph is a straight line. Okay. So let's put some values in this table so we can see what's happening here. Let's go ahead and we'll do 4 ordered pairs in there. Okay, so we have our first ordered pair would be -4, 1. So when your input's -4, your output's 1. And then your next point would be -2, 0. Next point is 0, -1. And your next point is 4, -3. Okay. So we're going to have to graph that. So this is the only graph you're going to do in your notes today. So do a decent job, okay? But let's set up an XY grid, coordinate grid. Always label the X and Y axis, always, always, okay? And then we're going to have to set up little tick marks to show what we're counting by. So one thing I do is I look at my table and the largest value is like 4 and -4. So that's as far out as I really need to go. So I can use the notebook lines to help me with that. All right. So this would be 1, 2, 3, 4, 5. -1, -2, -3, -4. Okay. And then you also have to do it on your x-axis. So just kind of try and do the same width as your notebook lines. 1, 2, 3, 4, 5. Okay. And I know I go fast because I've been doing this forever. So pause the video if you need to. I'm going to start though. Okay. So now we have our graph set up and we're going to see what this table of values looks like. So you need to remember that this right here is just an ordered pair. That's -4, 1. So I'm going to go to the origin. That's my starting position. -4 on the x tells me I go left 4. And then 1 on the y tells me to go up 1. So that's my first point. Second point is -2, 0. So I go to the origin, I go left 2, and then the 0 just tells me to stay. I don't go up or down, I just stay. So I'll put my point there. Next point is 0, -1. So I go to the origin. Now the first number is 0, meaning I don't go left or right at all. I stay on the y-axis, and I'm going to go down 1 since the y is -1. Okay, and they're looking like they're falling in a straight line so far, but we still have to check the last point. We have to check every point. Last one is 4, -3. So I start at the origin. I go to the right 4, since it's +4, and then I go down 3. Okay, now you could get a ruler if you wanted to, but remember we created this by hand, so it's not super exact, but you should notice that they all kind of fall in a straight line. Since these points fall in a straight line, it is linear, okay? So somewhere on here, tell yourself that, cool, it's linear, yay, okay? But I hope you're like, this Meineke, I feel like there's gotta be an easier way. Are you telling me that to check a table, I'm gonna have to plot the points, all the points, and see if they end up in a straight line? That's just one way, okay? But a better way to do it is by checking to see if there's a constant rate of change. So this next part is the meat of the lesson here. Okay? So instead of, you could do this, you could plot the points every time, but think about if your values were like -28, 1000. You would not want to draw a graph that big. What if you had decimals in there, -2.16, and 5.002. You would not want to graph those. So there's got to be a better way. So this is where we're really going to get into what a rate of change means, a constant rate of change. So here's the key here. Must determine if there is a constant rate of change. So that's what I'm going to teach you on this page, is how to determine if a table has a constant rate of change. Okay, so if a graph is straight, there's a constant rate of change. If an equation has the x raised to the power of 1, it's going to be a straight line. And a straight line means there's a constant rate of change. Okay, for a table, there's a little bit of calculations involved. So this next little piece might seem a little bit beyond where we're at, but it's what we're getting into in the next week. So I do want this in your journal, okay? So let's get kind of some math. Ooh, that's not rate. Sorry, that should be rate. It's so ugly. I'm gonna cross it out. It's bugging me. Rate of change. How we represent this in mathematics, and it's gonna look so weird. You're gonna put a little triangle y and divide it by a triangle x. Yeah, write it down, okay? This looks weird, okay, but we're getting into real algebra right here. This little triangle is the Greek symbol delta, and delta means change. So this is saying you take the change in y and you divide by the change in x. So let's go ahead and write that so you know what those little weird triangles mean, okay? change in y, and you're going to divide it by the change in x. Change in y divided by change in x. Okay? Okay. So this is overall what we're going to be doing for like the next 3 or 4 weeks. We're looking at change in y divided by change in x and seeing if it stays constant, stays continuous. So let's go ahead and look at our first table here. Set up your x, y, and let's give yourself 1, 2, 3, let's do 4 values in the table. Okay? If at any point I'm going too fast, just pause it real quick. Okay? So first table, I'm going to go first ordered pair is 2, 7. Next ordered pair is 3, 9. Next ordered pair is 5, 13. Next ordered pair is 7, 17. Okay. So here's what we're looking for. We are going to calculate the change in y divided by change in x. What the heck does that mean? Well, change in y means I'm going to look at the y values. And I'm really just going to focus on the first 2 y values. This one has a y value of 7. This one has a y value of 9. What's the change? From 7 to 9, how much did it increase or decrease? Well, from here to here, and I always do these little triangles, you're going to be doing them too. From 7 to 9, that was an increase of 2. So I'm going to write plus 2 right there. Okay? So from these first 2 points, from this point to this point, when I'm calculating change in y over change in x, the change in y was positive 2. Now I'm going to figure out the change in x. So I'm going to look at the x values. From 2 to 3, how much did it increase or decrease? From 2 to 3, it just increased by 1. So the change in x was positive 1. And now you're going to go ahead and simplify if you can. Positive 2 divided by positive 1, that's just 2 divided by 1, which is 2. Okay? But we have to check from point to point. So now we're going to go from 3, 9 to 5, 13. So now I'm looking at this change in y from 9 to 13. 9 to 13, that's an increase of 4. Uh-oh, that's different from here. Maybe that means it's nonlinear, but we gotta do the whole thing. We gotta see if it works out. So for this one, my change in y was 4. Now let's look at the change in x. From 3 to 5, that's an increase of 2. So the change in x was 2. Positive 4 over positive 2, that's just 4 divided by 2, which is 2. Okay, that's good news. This one simplified to 2, this one simplified to 2. So right now, there is a constant rate of change, but we're not done. We have to check the whole table. Okay, so we have one last thing to look at. From 13 to 17, the change in y would be 4. Now we have to divide it by a change in x. So that's from 5 to 7. From 5 to 7, that's an increase of 2. 4 divided by 2 is 2. Now, so here's what you look for. If all of these, if the change in y divided by the change in x, if all of them simplify to the same amount, that means it's linear. That means that there is a constant rate of change between x and y, between y and x. Okay, so here's what you're going to write off to the side. And this is kind of what you would write in for your entry test question. So you're going to write this statement. This is linear because there is a constant rate of change. Okay, so that's your statement. If this was your entry test question and I said, figure out if this is linear or not, this is the statement you would tell me. This is linear because there's a constant rate of change. Now, since there's a constant rate of change, you would actually state what the rate of change is. I'm just going to write ROC, okay? Rate of change. What do you think the rate of change is? 2. Okay, so then you could finish it up and say the rate of change equals 2. All right. Okay, let's do a couple more examples. Here's number 2. Set up your X, Y. Let's put 4 values in there. All right. Okay, here's your first ordered pair. 1, 4. 2, 7. 5, 16. And 7, 19. Okay. That's an ugly 4, by the way. All right, so in order to know if this is linear or not, we have to do this thing. Change in Y over change in X. So from the first point to the second point, we start with our Y values. Okay, the Y goes on top, all right? So the change in Y, it went from 4 to 7. That means it increased by 3. All right, so I'm going to put 3 up there. From 1 to 2, I'm going over to the X's, change in X. From 1 to 2, that's an increase of 1. So it looks like 3 over 1. What's 3 divided by 1? It's 3. Okay. Now, right now, I would really love for you to pause it. If you're like, I think I get this, try it out. Go ahead and do your next change in Y over change in X. See what it equals. Do your change in Y over change in X. See what it equals, okay? If you're feeling like you might know how to do it, pause the video here, try it out, okay? If not, stay with me. From 7 to 16, 7 plus 9, is that right? 7 plus 9, yes. 7 plus 9 is 16. Let's divide it by our change in X. From 2 to 5. From 2 to 5, that's an increase of 3. What's 9 divided by 3? 3. So far, so good. It's constant so far, but we have to check the whole table. Last one, 16 to 19. That's an increase of 3. From 5 to 7, that's an increase of 2. So my change in Y was 3, my change in X was 2. 3 divided by 2 is 1.5. So did this stay constant? No. So is this linear or nonlinear? This is nonlinear. So here's your statement. You would say this is nonlinear because there is because there is not a constant rate of change. Okay. If this does not stay constant, if it changes, it's not linear. If this was like 3, 3, 3, yeah, linear. But it's not, it changes. So if there's no constant rate of change, then it's nonlinear. All right. So this number 3 is going to be your practice question. All right. So this is what you're going to enter into the entry task. I'm going to give you a table. You're going to have to do this part of it. You're going to have to do the change in Y over change in X, and you're going to check to see if it's constant or not. If it's constant, you would say, this is linear because there's a constant rate of change, and you could even tell me what the rate of change is. Okay, and the reason why the rate of change was 2 is because all 3 of these simplified to 2, right? If this last little number here, if it was like 3 over 1, so maybe it went from 5 to 6, then it would be linear. But the fact that this screws it up, it's not linear, okay? And if it's nonlinear, then there is no rate of change. It's not constant. So number 3, you're going to do the math yourself, and then you're going to write a statement. It is linear because there's a constant rate of change, and the rate of change is blah, blah, blah. Or you're going to say this is nonlinear because there's not a constant rate of change. All right. So here we go. Set up your XY table. Give yourself 4 values. Here it is. First ordered pair is 0, -4, -1, 0, -3, 8, -4, 12. So you're going to do your change in Y over change in X from each point to the next, and you're going to see if it all comes out constant or not. All right, so the statement that you'll enter into your entry task is this over here. You'll type in that statement. It'll look either something like this or something like this. Okay, you got to do the math first though to figure it out. All right, good luck. We'll practice more in class, but try it out. Try it out. You'll get there. Thank you.